And the characteristics of radiation, electromagnetic radiation, that as they are related to atoms, is illustrated in these two pictures, which I've labeled flame tests. If you put small amounts of compounds of strontium in a gas flame, you get a bright red coloration. If you do the same thing with copper, you get a green coloration. And the interpretation of this, for our purposes, is that excited atoms, if you put an atom in a flame, it absorbs energy, it goes into an excited state, and when it drops down to the ground state, it releases photons. And you can see from these two pictures that the photons that come out of excited strontium atoms must have different frequencies or wavelengths than those that come out of excited copper atoms. If we look at a sodium street light, the yellow kind of street light, in the visible range from 400 nanometers to 750, it has only two flavors of photons that are produced. Both of them appear yellow to our eyes, and that's the reason the light from the lamp has a yellow coloration. This is different from either one of these, and it's beginning to look like each different kind of atom emits its own signature photons of different colorations. And so that these flame tests become like a fingerprint. And you'll see this in the laboratory. You can use flame tests to distinguish between certain kinds of metals like you could with strontium and copper here. Now the hydrogen atom is of interest here because we have questions about it. It has, in the visible part of the spectrum, it produces a set of 4 different photons. These photons, one of them has a wavelength around 408, looks like. Another one might be 432. Another one is up here above 480. And then there's one up here at 650 something. I can't really read that scale. And that set produces, to our eyes, kind of a bluish pink coloration. But what I'm trying to convince you here is that the different kinds of atoms produce different sets of photons. That observation has within it information about those atoms. There must be some kind of energy levels within the atoms that combine in ways to produce photons of different characteristics for the different atoms. So how could that be? Well, spectroscopists developed over this time period that we've been looking at, and they were able to historically notice that the lines, like those in the hydrogen spectrum, came in series. And each series looked like it followed a similar pattern. The lines in the hydrogen spectrum, for example, on the long wavelength side were widely spaced, and as you went to lower wavelength, the spacing gets smaller and smaller and smaller until finally it reaches a limit down here. That's called a series. And there's a mathematical description of the spacing within these lines. Now, hydrogen, it turned out, has some lines from a series in the visible part. Those are the 4 that we saw. And we have them in this part of this diagram. But there's also, out where we can't see, but instruments can, an ultraviolet series in the higher energy photons that you can't see it very well here. It's closely spaced together, but it has the same kind of pattern if you stretch it out, space it out. And then in the infrared, there's another one. And these are named for the people who discovered them. But what we need to recognize from this is that there's something about the hydrogen atom that produces these series of lines. And this was a great puzzle. This was a challenge to try to figure out what it was about atoms that could produce these mathematically perfect series. The first guy who got credit for making a big advance is this fella, whose name is Rydberg. And he was able to take the frequencies of these lines, or the wavelengths in this case, and develop an empirical equation. An equation which could be used to calculate the frequencies or wavelengths of any one of the lines in the spectrum of a hydrogen atom. I mean, any one. This is what his equation looked like. One of them, the wavelength of the photons for that particular line, is equal to a constant, R, another R constant. We got lots of those. This is called the Rydberg constant, times the quantity in parentheses 1 over an integer squared minus 1 over a different integer squared. And the relationships were such that if n1 is equal to 2, n2 could be 3, 4, and 5, and on up. And what you got was the wavelength of the visible series of the hydrogen spectrum. If you put in 2 here, and in 3, 4, 5, 6, and so forth, 3, 4, 5, 6 produced these lines. And the general restriction is that n1 and n2 are positive integers, and n2 is always greater than n1. This is easy to figure out because if it were the other way around, the term in parentheses would be negative, and as such, since this constant is positive, it would give a negative wavelength. And that's nonsensical. There's no way to have a negative wavelength, is there? No way to have a negative length of any kind, at least not in this world. This equation, if you put in the right combination of n1 and n2, could give you the wavelength to many significant figures for any one of the lines in the line spectrum of hydrogen. Well, you're going to have to use this, or at least this will be one choice of equations for you to use to calculate the wavelength of some lines in the hydrogen spectrum. Now, of course, if you have the wavelength, then you can use E equals hc over lambda to calculate the energy of the photons. So this is one. Questions on this one? I'm going to do an example shortly. Okay, remember the Rydberg equation is empirical. It's based on the data. He took the data and worked backwards from the data to get an equation that fit the data. Well, you may think, well, that's not science, is it? But it is science, because the equation has within it some insight, or at least we can get insight from that equation about what atoms must be like. And within this equation, this difference of two terms here is the source of the insight. Maybe it indicates that there are different states of the atoms described by these integers that are involved in the production of a particular photon. As good as this is, it does not tell us why the lines of hydrogen follow this pattern. And Rutherford's model didn't even predict there would be line spectra, so it's of no use to us at all. So some additional effort is required for us to understand this. And the first person who got credit for this, I'm going to do this example, and then I'll tell you about Niels Bohr. What is the wavelength in nanometers of the radiation released when a hydrogen atom changes from level n is equal to 5? This is in the Rydberg equation. And whatever it means, n is equal to 5 to n is equal to 2. And this is the Rydberg constant. So to answer this problem, we're going to take the value of N1 and N2. First of all, we have to decide which of these is N1 and which of these is N2. Then we're going to plug those into the Rydberg equation. The Rydberg equation solution will give us lambda in meters, and then we can convert meters to nanometers. Okay? So here's the Rydberg equation. R is 1.097 times 10 to the 7 per meter. And N2 must be greater than N1, so N1 will be 2 and N2 will be 5. Okay? Otherwise, we get a negative wavelength. So let's look at the term in parentheses first. We could do that. 1 over 2 squared then, minus 1 over 5 squared is 1 over 4 minus 1 over 25. That's 0.25 minus 0.040, and that's 0.210. That's the term in parentheses. Okay? So we plug that in. 1 over lambda is equal to 1097 times 10 to the 7 meters, Rydberg, meters to the minus 1, Rydberg constant, times the 0.21 here. And so that boils down to 1 over lambda is equal to 2.3 times 10 to the 6. And lambda then is equal to 1 over 2.3 times 10 to the 6, meters to the minus 1. And if we evaluate that, take the reciprocal of this number, we get 4.35 times 10 to the negative 7. And that's in meters now. Meters to the minus 1, reciprocal, that's in meters. Convert it to nanometers, multiply by 10 to the 9 nanometers over meters. And this turns out to be one of the lines, 435, I think I guessed at 432 or something like that, in those 4 lines of the visible spectrum of hydrogen. Calculation like this is just a plug and chug, but of course you need to remember the form of the equation, and you need to remember that N2's got to be greater than N1. Questions on this? All right. Now what I would like to do then is to pick up the story where we left off and talk about this one. This is a picture of Niels Bohr, and he turned out to be, at the time, a student of Rutherford's, in Rutherford's laboratory. He came to work with Rutherford. He was a very bright guy, and he was, by working under Rutherford's direction, he was able to come up with a model for the hydrogen atom that you might say loosely predicted the line spectrum of hydrogen. At least his model was consistent with hydrogen producing line spectrum. And this is what he did. The first thing he did was to accept the Planck-Einstein idea of quantized energy. And he applied this to the hydrogen atom, and he said the hydrogen atom must have only fixed energy states. Okay? The reason he said that was he couldn't come out with the line spectrum idea without that. Well, this didn't seem too unreasonable, given what had gone before. In his model of the atom, you probably remember from your high school work that each energy state that the atom, the hydrogen atom, could have, he represented by a circular orbit of the electron around the nucleus. Well, that's not unreasonable, given what was known at the time. He also attacked the main problem with the Rutherford atom, and he did it in a very surprising way. He said, according to conventional physics, hydrogen atoms, electrons, ought to spiral down into the nucleus. Remember, minus attracts plus. We thought that that would happen according to classical physics. But what he said was, hydrogen atoms don't obey the laws of classical physics, and if we have an electron that's in one of these fixed orbits, it'll stay there unless the atom absorbs energy or releases energy. Well, this was the biggest spot where his idea was different than classical physics, and many physicists dismissed it out of hand. But if you follow this idea through the way he did, his approach was to take these concentric orbits They were all in a plane, and do some calculations. These calculations are pretty simple. They're not too bad. When I took freshman chemistry, they made us learn them. And I think you can be glad you don't have to worry about them. But basically, they were balancing the kinetic energy of the electron with the potential energy of Coulomb's law. And he did it in such a way as he was able to come up with a set of concentric orbits. Here were the distances. He was able to calculate exactly where they were and how much energy the electron had while in every one of them. And he said, okay, the place where the electron is determines the energy of the atom. And when the electron is closest to the nucleus, that's the ground state of the atom. It can't go any further down, can't be more negative than the electron being in the ground state. But if the atom absorbs some energy from somewhere, like a flame or an electric arc, the transformation from the ground state up to an excited state is accompanied by the absorption of a certain amount of energy. And the energy difference from the ground state up to the excited state is the amount of energy the atom needs to accept in order to cause this change from the ground state up to an excited state. So the ground state in this case was what he would say was described by the n value called n initial, which is where the electron, the orbit where the electron was to start with, going to n final. So if the electron was in the ground state, n was equal to 1. And if it went up to the excited state where n is equal to 3, then n initial is equal to 1 and n final is equal to 3. And for that to happen, the atom had to absorb the energy difference between n is equal to 1 and n is equal to 3, whatever that was. Now, the magnitude of the photon energy then is exactly equal to the difference in energy between the two stationary states. And we could see the excitation of the atom by the addition of just the right amount of energy, or once we have taken away that extra energy, the electron can come down from the excited state to the ground state, or any state in between. And in doing that, the energy, the difference in energy has to be released by the atom, and that's where the photons come from. So, yes? Electromagnetic radiation. Oh, you mean the energy coming out? Well, she asked what form the energy was in, going in or out. Going in, it can be electrical energy, thermal energy, light energy, anything that will excite the atom. Coming out, it's always electromagnetic radiation. That's the line spectrum consists of, in each case, all of the photons that had a particular frequency. So there would be a whole bunch of them for all the lines in the hydrogen atom, and which ones they are depend on how excited each individual excited hydrogen atom was, where the electron was. So E of the photon in the process of relaxation of the atom downwards is equal to E final minus E initial, and that will be, if E final is larger than E initial, then the electron's moving down, and if it's moving down, it's releasing energy as photons, and E of the photon is equal to H nu of the photon. And if we want it in terms of the wavelength, it's hc over lambda. So the energy of the photon is, in magnitude, equal to the energy difference experienced by the atom, delta E of the atom. We'll see more about that in just a minute. There's a diagram in your book that illustrates sort of the same thing from a slightly different perspective. Here are the Bohr orbits, and the one that's closest to the nucleus is n is equal to 1, and then the next one's n is equal to 2 and 3 and 4 and so forth. And what we see here are transitions. that would occur from various different excited hydrogen atoms. For example, this yellow line right here would come when an electron in an excited hydrogen atom was occupying the n is equal to 4 orbit, and it fell down to the n is equal to 2 orbit. That would produce photons of the right frequency for something approaching yellow light. Okay, and the 4 of these that you see here are intended to represent those 4 lines in the visible part of the hydrogen spectrum. Now this is shown on an energy level diagram over here. This is energy units in joules per atom plotted upwards. And the visible part of the spectrum is over here, and you see it's made up of transitions from higher levels, 3, 4, 5, 6, to 2. Well, where did we just see that? That was in Rydberg Equation, right? We said that the visible part of the spectrum wavelengths could be predicted by setting N1 equal to 2 and then N2 equal 3, 4, and 5. Okay? So there it is. And if we go to transitions down to the ground state, N is equal to 1, the energy of those transitions, 2 to 1, 3 to 1, 4 to 1, it's all out in the ultraviolet. So we can't see that. That has to be measured by a spectroscopist. But when we do it, it produces exactly the observed part of the spectrum, the line spectrum of hydrogen in the ultraviolet part of the spectrum, around 100 nanometers. Okay? Lower wavelength than the visible range, which drops off at around 400. So that's higher energy. And so the atomic spectra of any atom consist of only certain lines because the atom's energy can only have certain values. So if you accept the idea that the atom's energy is quantized, can only have certain values, then it follows from that, according to the Bohr model, that line spectra should exist, and these can be, the characteristics of them can be calculated. Questions on this? Yes, go ahead. She said, does each atom have its own set of these energy levels? And according to Bohr, they did. He didn't get it quite right as far as what the values were, though. But now quantum mechanics does get it right. And so the answer to your question is yes. Each atom has its own set of atomic energy levels. The quantum mechanical model doesn't view them as being circular orbits, but we'll talk more about that later. All right, so here's a problem. For the energy of the n is equal to 1 level of a hydrogen atom, the energy is negative 2.18 times 10 to the minus 18 joules. And the n is equal to 2 level, the first excited state, this is a ground state, first excited state is minus 5.45 times 10 to the negative 19 joule. Calculate lambda in nanometers of the photon emitted when the transition is n is equal to 2 to n is equal to 1. This is n is equal to 2, this is n is equal to 1. So if we look at this, E of the photon is equal to h nu is equal to hc over lambda. We saw that before. And since this is an emission, that is to say, the electron is moving downward, n is equal to 2 to n is equal to 1, that causes energy to be emitted. So we call it an emission spectrum. In emission spectra, E of the photon is equal to minus delta E of the atom. That is to say, the atom's energy change is negative. But the E of the photon can't be negative. Okay? Photons have to have positive energy, it's like positive wavelength. So there has to be a sign difference between these two. E of the photon has to be minus delta E of the atom, which would be minus E of the final state minus E of the initial state. Okay? If we want to calculate the lambda, we're going to have to determine the energy E of the photon and sort of work backwards. Here's how I would suggest that you do it. First of all, delta E of the atom is equal to E for n is equal to 1, the final state, minus E of n is equal to 2, the initial state. All right? So this is equal to, we're given the numbers here, negative 2.18 times 10 to the minus 18th joules, then minus quantity, minus 5.45 times 10 to the 19th, negative 19th joules. So delta E of the atom, once you plug this into your calculator, turns out to be negative 1.64 times 10 to the minus 18th joules. This is delta E of the atom. So E of the photon is equal to minus delta E of the atom. So that's equal to plus 1.64 times 10 to the minus 18th joules. Does that make sense so far? Questions? Okay. Now we have E of the photon. All we have to do now is to calculate the wavelength. Lambda of the photon is equal to E of the photon divided by hc, right? And that is 160, I'm sorry, I've got it upside down. Lambda of the photon is on the bottom here. So if I multiply both sides by lambda of the photon, hc is going to be on top and E is going to be on the bottom, so please correct that right there. This is going to be hc over E of the photon. Sorry, I'll get back in the swing of things here in a minute. So let's plug in the numbers. H is 6.63, the three significant figures, times 10 to the minus 34 joule seconds. C is 3.00 times 10 to the 8th centimeters per second. E is 1.64 times 10 to the negative 18th joules. Okay, so this is lambda, and lambda is going to come out in, this should be meters per second right here. I don't know what that little squiggly mark was I put there. Lambda is going to come out in meters, and the number that I got was 1.21 times 10 to the negative 7 meters. And this asks for nanometers, so we multiply this by 10 to the 9th nanometers per meter, and we get 121 nanometers. So this is working backwards from the energies to the wavelength. Do you have a question about it? Okay, good. If you're comfortable with that, now, I want to talk about then how Bohr handled the energy of the his orbits in his model. Okay, if you've got this copied down, sorry for getting it upside down. Bohr said that in his model, which he derived, he just didn't pick this out of the air, any one of the stationary states, the orbits, had an energy equal to negative 2.18 times 10 to the minus 18 joules times the quantity 1 over its value of n squared. So if n is equal to 1, the hydrogen atom's in the ground state, then the energy of the hydrogen atom is negative 2.18 times 10 to the minus 18 joules times 1 over 1 squared. So that's negative 2.18 times 10 to the minus 18 joules. That's the ground state of the hydrogen atom. Notice that it's a negative value. The energy of the hydrogen atom doesn't get up to 0 until n gets up to infinity. So n would have to be very large, and anything less than infinity, E would be negative, but when electron is fully removed from the nucleus, that would be equivalent to saying it's gone off to infinity. Okay? If that were the case, then its energy at that point would be 0 relative to the scale that we're using. So E will be negative for all values of n below infinity. The transition energy then can be calculated by delta E of the atom is equal to E final minus E initial, and E final is the n value for E final is going to be plugged into this equation, and the n value for this E initial is going to be plugged in, and if you factor out the negative 2.18 times 10 to the negative 18 joules, Bohr's delta E equation is given here. 1 over n squared final minus 1 over n squared initial. Notice how much that looks like whose equation? Rydberg. It looks a lot like Rydberg's equation. The constant here is different because we're getting delta E of the atom, not 1 over lambda. But the shape of it, the general appearance of it looks very similar. So this is Bohr's equation for calculating the energy of the change in the energy of the atom. And of course, remember, that's equal to minus E of the photon. Okay, so let's do this one. Calculate the energy change in joules that occurs when the electron falls from Ni is equal to 5 to Nf is equal to 3 in the hydrogen atom. And we're going to use Bohr's equation for this. Okay? So the energy change is delta E of the atom, and that is equal to negative 2.18 times 10 to the minus 18th joules. And you need to memorize this equation too, times 1 over n final squared minus 1 over n initial squared. So that's equal to negative 2.18 times 10 to the minus 18th joules times final is 3, 1 over 3 squared, minus the initial, which is 5, 1 over 5 squared. And the next step is negative 2.18 times 10 to the negative 18th joules. Making my hand tired just to write it. Times 1 over 9 minus 1 over 25. I suggest if you get equations like this on a different place in the paper, you evaluate what this parenthetical term, what the magnitude of it is, like we did just before this, and then multiply it here. This is negative 2.18 times 10 to the minus 18 joules times 0.111, the three significant figures, minus 0.040. And when I got rid of that, I got negative 1.55 times 10 to the minus 19th joules as delta E of the atom. Delta E of the atom. Questions? Yes, go ahead. Question? Just stretching your arm. Okay. All right. Other questions? All right, so that's how Bohr's equation works to get delta E of the atom. But you're hardly ever asked for delta E of the atom. There are very few questions for that. Most of the questions have to do with what's the wavelength, what's the energy, what's the frequency of the photon. So, here's the next one. Calculate the frequency of the photon released when the hydrogen atom transition from n is equal to 5 level to n is equal to 3 level occurs. Well, that's the same transition we just looked at, right? Very same one. So, we'll write down E of the photon is equal to minus delta E of the atom. Remember, this is sort of like heat lost equals minus heat gain. Same kind of thing, really. And this will be, since it's E of the photon, h nu of the photon. And that will be equal to, from the previous page, 1.55 times 10 to the minus 19th joules. Okay? So, solving for nu of the photon, in this case, is going to be equal to E of the photon over h. So this is 1.55 times 10 to the minus 19th joules over 6.636 times 10 to the minus 34 joule dot seconds. Plug all that into the calculator. Question?
Isn't that 6.626?
I'm sorry, 626. Thank you. 626. You can either use 6.63 if most of the other numbers are to 3 significant figures, or if they're to 4, you have to write it all out, 6.626. Thank you. And when I got that into my calculator, I got 2.33 times 10 to the 14th hertz. Okay, nu of the photon for that particular transition. And you could look on the electromagnetic spectrum and see where that shows up. Okay. All right, so that was the Bohr model. Now, that's all the good news. The bad news was that Bohr's model refused to give the right answer for helium or lithium or anything else in the periodic table. And the best physicists in the world did everything they could to modify it because it was so beautifully simple. And it would be so nice if that was the way we could explain everything. I act like I'm there. I've always been fascinated by the story of quantum mechanics development because quantum mechanics is the most successful scientific theory, in my opinion, that we've ever run onto. So Bohr's model failed. It failed, and it simply would not work for anything that had more than one electron. And that shouldn't be too surprising because he had no way to evaluate the electron-electron interaction. So Bohr's model had to be thrown out, but they kept the idea of quantized energy levels from it to go on further.